given to you in the table. K2, you should be taking this from the standard. And then you have to find out the short term, the long term. The formulas are given again, the load combinations are given to you, what to use. Then the reflection formula is given to you. Find out for short term, check it against the limit. Then the long term, check it against the limit, whether and then comment if it's okay. So in this case, the reflection is within the limits for both short and long term reflection, and is okay to use the section. So that's all about the timber glue lane beam. So, you know, I mean, doesn't matter how tricky I make it, the procedure is still the same, right? So there is no here and there. We just follow the standard, follow the step, all the necessary formula, everything will be given. So there is no, it's not rocket science. Then the last question in that exam, before we move on to the next one. Question 5, it was a radiator of energy at grade, dry condition 150 by 150 or 140 by 140, that's the actual size. Column of height 2.7 meter between floor levels, pin at the base, and supports 8 square meter of flooring. So 8 square meter, that does mean something, right? So when you're not given a point load, don't get shocked. Go in this case, is the area is given, the load will be given to you in the kPa. All you have to do is just multiply. So you can see here, G is 0.5 kPa and Q is equal to 2 kPa. All you have to do, 1.2 G, just find out the load, what is that load. Then the tricky part in this one is, there is an eccentricity, exactly the same example we did in class. So there is an eccentricity of 50 millimeter. So now, in this case, so what we have a column. So everything has a centroid. So if I do a cross section of it, that's the centroid as the center of mass or center of area. That's the centroid of the section, right? It's always whether it's this pin, it should have a centroid. We can calculate it. We have 3D software these days. We just draw the 3D shape of it, and it will give us the centroid wherever from each direction. Where is the centroid? The center of this, the mass, the center of mass for this pin, right? And it's very important in the buildings. Center of mass, two things to remember: center of mass and center of stiffness. So stiffness means the resistance system, and mass means the weight of the building, and it's quite critical in earthquake. If those two, if we don't have a symmetric structure, our resistance system, lateral resistance system like shear wall or portal frames, if they're not evenly distributed, then what we have? We have the center of stiffness to one side of the building, and the center of mass is usually in the center of the building, right? Because the floor is all over uniform most of the time, except you might have a few walls here and there which will slightly offset from the center of mass, but it's, in most of the cases it's like within 10% of the 10 to 15% of the center, right? The dead center. Or if it's a rectangular building or a curved building, it's a different issue. But as soon as you offset those two things, the center of mass and center of rigidity, there become an eccentricity. And then in terms of, let's say you have earthquake and you have big buildings, you have 10,000 kilonewton force, even if it's 1 meter, what happened? 10,000 kilonewton meter additional moment to be resisted by the lateral elements, right? So it makes huge difference. Therefore, you will see this center of mass and center of rigidity a lot. So in this case, what we have the center of, so centroid is somewhere there, but the load is slightly off center, right? That means the beam is side fixed somehow, but the load is not, and there is an eccentricity. What does that eccentricity do? It creates a moment in that column, right? Like the connection meter. So, and here you have to consider that moment. Mr. King, please don't put it on YouTube, okay?
Oh, no.
I'm not an actor.
Not my phone, so it's all
Okay.
good.
Whose phone is this? Don't put it on YouTube, okay? or Facebook because
For
you
your
don't have
support.
permission.
Yeah.
Okay.
Literally what he said. Hey.
So then, okay, so let's go to the solution. We have G, Q, height, and tributary area. So that means the load combination NC, which is we are interested in a column because it's a column, so we need to find out the axial load. So that axial load become equal to 1.2 G plus 1.5 Q times the tributary area of that column. So now this column here, what is the area it is supporting? So for example, looking at a plane, let's say the column is here somewhere and it is supporting a beam from this direction or this direction, and let's say there is a column there, a column here, a column here. So simple, it is, that is half each way. And this here is 8 square meter, that area, right? That's how it works. So now I've been given the loads in kPa, which is pressure on the area, and I just have to convert that to a point load on this column here. What is that point load? So that's what I have done here. It has become 28.8 kilonewton of axial load. Then eccentricity is given, so the moment is equal to NC times EX, and it's 1.44 kilonewton meter. Of course, it's, you know, it's not a huge moment, but it's timber. We're not in steel anymore or concrete, so it could create a lot of trouble. And let's see what happens. So B is 140, D is 140, FB is equal to 14. Remember, it's a dry condition. If it was wet condition, then this would be 11.7 or lower, or depend on the timber grade. FS, that's the shear strength, 3.7, FC 18 MPa. Again, if it was wet, those might have different. So the first one is the moment capacity. I won't go too much into detail. There's the formula. We find out the section modulus. Reduction factor K1 is 1.2 G, so we will consider the combination as the medium term combination. So that's 0.8 K4 because it's one member. It's only one member. You know one member, right? There's no, the actual section or the column is not made of multiple members. If it was multiple members, then what we had to do? No, I'm talking about K4. You're not concentrating. If it's multiple member, K4 is the parallel support factor, right? So if we have more than one member, then we increase, right? And that's why in this case, because it's 140 by 140, it's square one solid section. And if there is, why do we increase this? Usually in timbers we have defects, right? So if we have more members, so if it's one member we don't usually increase, but if we have more members, so there might be less defects, or the defects will not be concentrated at one point. For example, if there's a column and there's a knot here, it's weakening the entire section, isn't it? But if I had two, let's say for example, two members, and let's say there is a knot, but we got a stronger member next to it, right? Another one. So we got two members, and these defects are staggered over the length. They are not concentrated in one place. Like if it's one member, if there is a knot, that could be going through the entire section. While if we have more than one member, these defects are distributed. If they're staggered, they're not at one location. So you have one member stronger, even if there's the defect and the other one, you got another one. So that's why we take into account for that one. That's the purpose of doing this. Then similarly, LAY in this case, there is no restraint, it's a column, it's just equal to the height of the column. And it's a square section. Whenever it's a square and round. Sorry, sometimes I had to work hard to, So when it's a square and round section, simple. S1 will give you 0 or infinity, and that means K8 is equal to 1. Because it's not prone to buckle. It just will maximize the capacity. But not an axial. Axial is different thing. Only for bending. If it's a square and or round section, it will be 1. Then the moment capacity we just did, and it is okay. It is only 4.098 kilonewton meter. Now I have to go to the axial capacity. So in this case, it's a square, and the effective length in both direction is exactly the same. There is no restraint at the mid height, right? So it is only restraint at the top and bottom. So our effective length is the same. So therefore, NCX is equal to NCY. But if I would have given you the condition that okay, in the Y one direction there is a restraint, for example, here, it hold it, then we split the heights. But again, this is a square section, so your worst case is again that direction that you are considering, right? But maybe the movement is not in that direction. You know, the movement is in the direction that is restrained. So you have to be careful and you know, use your knowledge and judgment, whether it's making it worse or making it good. So in this case, we don't have any restraint, so we don't need to worry. NCX is equal to K1, K8x. So in here, when we go to axial, now we will have K8 for x direction and y direction. And that simply depend on the effective length or segment length in x direction and y direction. So in this case, we just only one. So it doesn't matter. K10. K10, that is what we need to find out the effective length. So K10, in our case, it's pin, so it will be 1. You can go to the table, you will be given those figures. It's exactly the same as like steel columns, different cases. So you have to go and pick what case you are in and choose that factor there. Then LAX is equal to that. S2 is LAX divided by D, and for Y it would be LAY divided by B, one or another. So then NCX, therefore K8 is equal to 0.43. You can pick this from the table, or you can use the figure. You know, the first figure, you can use that one and find that out. Or alternative easy way is just to use tables. And that's, the capacity is okay. Now the last thing I need to do, and now I have two actions, so I need to check the combine. And the combine check is that one there. Mx divided by Mn, Nc divided by N, that should be less than or equal to 1. And that's the end of the exam. We did it in 1 hour.